Okay, so this next section I've actually broken down into 3 bits because it's so big. We're going to be using some of the ideas we picked up in the last topic and applying them to actual industrial processes and sort of longer questions. So these are things you're going to pick up by the end. We're going to learn these terms: limiting, reactant in excess, and we're going to learn a little bit about percentage yield as well. I'm going to start just by looking at this term stoichiometry and what it means. So if we look at the equation, you've got these numbers in front, these coefficients that we use to balance the numbers, the formulae, sorry. And you can see here you've got 2 moles of sodium reacting with 2 moles of water to produce 2 moles of sodium hydroxide and 1 mole of hydrogen. Second one, you've got 2 moles of hydrogen reacting with 1 mole of oxygen to produce 2 moles of water. Now, what we'll find is that during the course of a reaction, one of the reactants will run out before the other one, right? And that will ultimately determine how much product we get. So for example, if we look at the second reaction, so we've got a little test tube of hydrogen in our lab, which has got loads and loads of oxygen in it. It would make sense that our hydrogen is our limiting reactant, and by understanding the number of moles of hydrogen that we've got, we can work out how much of the product we should be making. So this becomes our limiting reactant, is the important one in determining how much product we get. Now, this slide, one of the most important ones in the unit, we've got 3 steps highlighted here. And these 3 steps are going to be important time and time again. All the calculations in this topic 1.3 will involve this, followed by this, followed by this. So take the information you've got, go into moles. Second step, that's when you look at your equation. Look at the stoichiometry and see how things are reacting. So the second step is to look at the equation and see how things react. The third step, once you've worked out how many moles of product or whatever it is you're going to get, you can convert back out of moles. So first step, go into moles. Second step, look at the equation. Third step, come back out of moles into more user-friendly terms, as it were. So here's an example. It's assuming that we've got an excess of this, so we're not really very interested in the carbon dioxide. There's plenty of that around. We've got 320 grams of this. We want to know how much iron we're going to make. And so step 1, take the information you've got, convert it to moles. There we go. Step 2, look at the equation. What's the mole ratio? Well, it's 1 to 2. So if I'm in my situation dealing with 2 moles, I'm going to end up making 4 moles. Well, how heavy is 4 moles? That's step 3, convert back out of moles. And there we go, using this relationship throughout, we're going to get 224 grams. Now, that was good. Here we assumed that this was, what we'll say, in excess. There's more than enough of this to react with all of this. Very often in a question, we won't know which is the limiting reactant, which is the reactant in excess. And to do that, to work out which is limiting, we just go through those same 3 steps again, using the information that we've got. So we pretend we don't know this to begin with. 39.75 grams of copper oxide, and you can convert that to a number of moles. You can look at the mole ratio, which is 2 to 1, and you can decide how much carbon you would need to react with that. Check how much carbon you've actually got. Is there enough? Is there not enough? Which is the limiting reactant? So have a read through that. And then once you've worked out which the limiting reactant is, which it looks like it's copper oxide, that will determine how much product you're going to make. And it's just then like the last question. Again, 3 steps coming in that you can follow through. Right, this slide introduces the idea of percentage yield. And we'll ignore this bit to begin with, and indeed that bit, and we'll just treat it like we did a question or 2 ago. We'll try and work out how much iron oxide we should be getting based on these amounts. Now it says they're in tons, pretend it says grams. makes it a bit easier for my maths, and I can just change the G to a T at the end. So we've got to work out which is the limiting reactant to begin with. So I've got 50 tons, 50 grams of iron 2 sulfide. There we go. That weighs, that's a 1 mole, 119.96. So if I convert that to a number of moles, 50 divided by 119.96, that is 0.417. Looking at that, how that reacts with the oxygen, it's a 4 to 11 mole ratio, so it's 1 to 11 fourths, which would mean my 0.417 would react with, multiply that by 11 divided by 4, that reacts 1.146. So that's how many moles of oxygen react with that amount of iron 2 sulfide. What does that come in as in terms of an actual mass? Well, the mass of 1 mole is 32, so we multiply that by 32, that comes to be 36.7 grams of tons. So do I have 36.7 tons of oxygen? No, I've only got 10. So that means my oxygen is my limiting reactant, and that's going to be the one that determines how much product I make. So now that we know that, we can go back and say, right, 10 tons of oxygen, 10 divided by 32, that's my number of moles of oxygen, which is 0.3125. Mole ratio, horrible mole ratios in this question, 11 will give me 2, 1 would give me 2 over 11, so 0.3125 is going to give me 0.057. So I need to then convert that to a mass. Again, that was kind of my first step, second step, third step, and the mass of 1 mole of Fe2O3 is 159.68, which means that's going to be so I should be making 9.07 tons. Question tells me I'm actually making 7, so my percentage yield is the amount that I've made divided by the amount that I could have made, expressed as a percentage. So my percentage yield is 77%. Right. I've not been very careful at all with significant figures, so that's something to look at when we talk about topic 11. But this is how I've managed to work out percentage yield. It is my actual divided by my theoretical as a percentage. So this gives me 77% yield. Another example, this time they've been kind, you don't have to work out which is limiting. We can just go through the motions again. You might want to pause me and then have a look at my working. So we've got 2.5 grams of aluminium. This is the first step, aluminium 26.98. So step 1, convert to moles, 2.5 divided by, it's 0.0927. Excess oxygen, so that's fine. Produce 3.12 grams of aluminium oxide. Well, we're working out percentage yield. So work out the theoretical yield first. How much should we be getting? So it's a 4 to 2 ratio. So that's going to be 1 to a half, which means my 0.0927 should be producing for me 0.0463. And then, so that was step 2, step 1, step 2, step 3, come back out of moles. So I'm dealing with aluminium oxide. Number of moles is mass divided by mass of 1 mole. The mass of 1 mole is 101.96. So that means I should be making 4.72. I've ended up actually, the actual yield is 3.12, so my percentage yield, 3.12 divided by 4.72 as a percentage. And this time I've got 66%. Alright, so we've covered limiting reactants, reactants in excess, and this idea of a percentage yield. Very important concepts for industrial chemists as they work out how much they are trying to produce or how much they're making in their processes.